The temperature readings coming out of the American Southwest right now are not a weather story. They are a physiological warning, an infrastructure stress test, and a food security alert wrapped into a single, suffocating event. Dozens of cities have already shattered all-time heat records in the past 30 days, and the models projecting what comes next are not showing relief. They are showing more. By the end of this video, you will understand exactly what this heat is about to do to the country and why the scientists watching it are more alarmed than the headlines are letting on. Welcome to the Space Desk. Let's get into it. The numbers that should scare you. Let's start with the raw data, because the raw data is genuinely hard to look at. Phoenix, Arizona, hit 113 degrees Fahrenheit on 11 consecutive days in late June of 2026. That is not the record-breaking part. Phoenix hits 113. Phoenix is used to 113. The record-breaking part is that the overnight low during that same stretch never dropped below 92 degrees. 92 degrees at 3 in the morning, the overnight low, the period that is supposed to give your body, your home, and your city's infrastructure a chance to recover. It did not recover. Las Vegas recorded 117 degrees, tying its all-time record. Tucson broke its June record by 3 degrees, which in climate science terms is not a near miss. It is a hammer blow. Palm Springs hit 122. And here is the number that should reframe all of those. The average high temperature in Palm Springs in June is 108 degrees. 122 is not a hot day in Palm Springs. It is 14 degrees above a baseline that is already one of the hottest sustained climates in the continental United States. Now move east, because this is not a desert story. Dallas recorded 10 consecutive days above 107 degrees. Kansas City, which sits in the middle of the country and has absolutely no business being discussed in the same sentence as Phoenix, hit 104. Memphis hit 106. These are not cities built for this. Their infrastructure, their housing stock, their vulnerable populations, none of it was designed around the assumption that the American Midwest would start feeling like the Sonoran Desert in late June. The National Oceanic and Atmospheric Administration has officially logged June of 2026 as the hottest June ever recorded in the contiguous United States. Not the hottest in recent memory, the hottest in the entire observational record, which stretches back to 1880. That record stood for 146 years before this month erased it. And the models are not showing a cool down. They are showing a second pulse. What record heat actually means scientifically. Here is where I need to slow down for a second, because the number on your weather app is doing you a disservice. When your phone says it is 104 degrees in Dallas, that is the air temperature measured in the shade at a standardized height with no accounting for humidity. It is a real number. It is also an incomplete number. And for understanding what heat actually does to a human body, incomplete is dangerous. The measurement that matters is the wet bulb temperature. You can think of wet bulb temperature as the temperature that accounts for both heat and humidity simultaneously. It is called wet bulb because the original way to measure it was to wrap a thermometer in a wet cloth and let evaporation cool it. The temperature that wet thermometer reaches is the wet bulb temperature, and it tells you something the dry thermometer cannot. It tells you how well evaporation works in this particular air. Why does evaporation matter? Because evaporation is how you cool down. It is the entire mechanism behind sweating. Your body pushes moisture to the surface of your skin. That moisture evaporates, and the phase change from liquid to vapor pulls heat away from your body. In dry desert air, that process is extraordinarily efficient. You sweat, it evaporates almost instantly, and you feel cooler. In humid air, the atmosphere is already so saturated with water vapor that your sweat does not evaporate efficiently. The cooling system slows down. At high enough humidity combined with high enough heat, it stops working almost entirely. The heat index, which is what your weather app usually displays as the feels like temperature, is an attempt to capture this effect. And the heat index numbers coming out of the South and the Midwest right now are extraordinary. Dallas has registered a heat index above 115 degrees. Kansas City hit a heat index of 112. Memphis, where the humidity is already brutally high even on a normal summer day, has recorded heat index values approaching 120 degrees. 120 degrees is not a temperature the human body was built to tolerate for extended periods. And unlike the desert Southwest, where the dry air at least gives your cooling system a fighting chance, the humid Southeast and Midwest give you none of that margin. You feel hotter than the thermometer says. Your body works harder to cool itself, and the air it is fighting against is not cooperating. I will say this plainly. The number on your weather app is the optimistic version of how hot it is. The human body has a hard limit, and we're approaching it. There is a number in thermal physiology that almost never makes the weather broadcast. That number is wet bulb 35 degrees Celsius on the wet bulb scale. And it is not just a bad day. It is the theoretical ceiling of human survivability. At wet bulb 35, a perfectly healthy adult sitting completely still in the shade with unlimited water cannot stop their core body temperature from rising. The cooling system does not struggle. It quits. Heat exhaustion becomes heat stroke, becomes organ failure in hours. For most of recorded history, wet bulb 35 was considered essentially theoretical. A line on a chart the real atmosphere almost never crossed. That assessment has been quietly revised. Researchers have documented wet bulb temperatures touching 35 in parts of South Asia and the Persian Gulf within the last 5 years. The United States has not crossed it yet, but wet bulb readings in the low 30s have been recorded along the Gulf Coast. The trend line does not point down. We already know what happens when heat like this meets a population that never saw it coming. In 2021, a heat dome settled over the Pacific Northwest. Portland hit 116 degrees. Seattle hit 108. In 4 days, more than 1,200 people died across Oregon, Washington, and British Columbia. Most of them died indoors, in their bedrooms, in front of fans that were moving air too hot to help. That last part matters. Heat is the deadliest weather phenomenon in the United States most years, killing more people than hurricanes, tornadoes, and floods combined. It just does it invisibly, behind closed doors, in unair-conditioned apartments on upper floors, in the bodies of elderly people who checked the weather app, saw 104, and decided that was manageable. It was not manageable. It just did not announce itself. The infrastructure nobody talks about here is something that does not get discussed enough when heat events make the news. The human body is not the only system that fails under extreme heat. The physical infrastructure of the United States, the power grid, the road network, the rail system, the water distribution system, all of it has operating tolerances. And several of those tolerances are being approached or exceeded right now. Start with the power grid, because the power grid is the system that everything else depends on. Air conditioning runs on electricity. When temperatures spike across a large region simultaneously, every air conditioner in that region runs at maximum capacity at the same time. Electricity demand spikes to levels the grid was not necessarily designed to meet. Transmission lines, which carry electricity from generation facilities to homes and businesses, are made of metal. Metal expands when it heats up. When transmission lines overheat, they sag. When they sag far enough, they contact trees or structures, and they trip out of service. The grid begins shedding load. Rolling blackouts begin. And the moment the grid fails, every air conditioner in the affected area stops running. In February of 2021, an extreme cold event knocked out Texas's power grid for days, killing more than 246 people. The grid failed in winter. The same physical vulnerabilities that caused that failure aging infrastructure, inadequate weatherization, a system built to handle average conditions rather than extremes, are present in summer. The summer version of that failure is a heat event knocking out power across a region where the outdoor temperature is 107 degrees and the indoor temperature without air conditioning climbs toward 120. Road surfaces have a design temperature. Standard asphalt is typically formulated to withstand temperatures up to about 140 degrees Fahrenheit at the surface. In direct sunlight on a 115-degree day, asphalt surface temperatures can exceed 150-160 degrees. Roads buckle. Runways at airports have been temporarily closed due to surface deformation during recent heat events. Rail lines, which depend on precisely maintained gaps between sections of steel track to allow for expansion, can buckle when those gaps close and the steel has nowhere to go. Train derailments caused by heat-buckled rails are not hypothetical. They have occurred in the United States and in Europe during recent heat events. Water systems lose pressure when demand spikes. Everyone showers, everyone fills pools, everyone runs sprinklers simultaneously, and the distribution system cannot keep pace. In some heat events, water pressure drops low enough that fire hydrants cannot deliver adequate flow. That is not a theoretical inconvenience. That is a fire department responding to a heat-related fire in a building where the hydrant pressure is insufficient. The American Society of Civil Engineers' most recent infrastructure report card gave the United States a C- overall. That grade was assigned under normal operating conditions. Extreme heat is not a normal operating condition. It is a stress test applied to a system that was already marginal. Why this heat is different, the science of heat domes. You have probably heard the term heat dome in weather coverage over the last several years. It has become almost ubiquitous to the point where it starts to feel like meteorological wallpaper. So let me tell you what it actually is, because the mechanism behind it explains why these events are becoming longer, more intense, and more geographically expansive. A heat dome forms when a large area of high pressure in the upper atmosphere essentially parks itself over a region and refuses to move. High pressure systems cause air to sink. Sinking air compresses, compressing air warms. This is basic atmospheric physics, the same reason a bicycle pump gets warm when you use it rapidly. The air descending inside a heat dome warms as it sinks, and it traps the hot surface air below it, preventing the convective processes that would normally mix the atmosphere and allow some of that heat to escape upward. The result is a sealed environment where heat accumulates day after day with no release. This mechanism has always existed. Heat domes are not new. What is new is the duration and the intensity of the events, and the explanation for that change runs through the Arctic. The jet stream is a river of fast-moving air in the upper atmosphere that circles the northern hemisphere and largely governs where weather systems go and how long they stay. The jet stream is driven by the temperature contrast between the frigid Arctic and the warmer mid-latitudes. A large contrast means a fast, tightly wound jet stream that moves weather systems through efficiently. No single system, including a high-pressure dome, lingers too long before the jet stream pushes it along. The Arctic is warming at roughly 2 to 4 times the rate of the global average. This is one of the most documented and replicated findings in climate science. As the Arctic warms, the temperature contrast that drives the jet stream weakens. A weaker jet stream is a slower, wavier jet stream. It meanders. It develops large loops and bends that can become stationary, holding weather patterns in place for days or weeks at a time instead of moving them through in days. A heat dome under a sluggish, distorted jet stream does not get pushed out in 4 days. It sits. It bakes the region below it for 10 days, 12 days, 2 weeks. The city of Phoenix did not just hit 113 for a day. It hit 113 for 11 consecutive days with no nighttime recovery because the atmospheric pattern holding the heat in place was not going anywhere. The scientific literature on this connection between Arctic amplification, jet stream behavior, and the persistence of extreme weather events is substantial and growing. it is not settled in every detail. There is genuine ongoing debate among atmospheric scientists about the precise mechanisms and the degree of attribution. But the observed trend is not in dispute. These events are lasting longer than they used to, and the physical mechanism that explains why is operating in the direction that makes that trend worse, not better. Agriculture on the Edge, I want to talk about something that will not affect you this week, but will absolutely affect you in 6 to 8 weeks, and probably sooner. And that is what this heat is doing to the food supply. The United States is the world's largest exporter of corn and soybeans. The Corn Belt, which spans Iowa, Illinois, Indiana, Nebraska, Minnesota, and parts of surrounding states, is one of the most agriculturally productive regions on the planet. And the Corn Belt is currently experiencing heat stress at a critical point in the growing calendar. Corn is particularly vulnerable to heat during pollination, which for most of the Corn Belt occurs in late June and July. Pollination is the moment when the corn plant transfers pollen from the tassel at the top of the stalk to the silk, emerging from each developing ear. It is a narrow window, roughly 2 to 3 weeks per field, and it is extraordinarily sensitive to temperature. When air temperatures exceed 95 degrees Fahrenheit during pollination, pollen viability drops sharply. The pollen desiccates, the silk dries. Kernel set, the process by which each pollinated silk becomes a kernel of corn, is dramatically reduced. A field that should yield 200 bushels per acre might yield 140 or less. The plant did everything right. The heat just arrived at the worst possible moment. Soybeans are somewhat more temperature tolerant, but they face their own critical window during pod fill, which runs through July and August. Sustained heat above 90 degrees during pod fill reduces seed size, reduces oil content, and reduces total yield. Livestock are simultaneously under extreme stress. Cattle, particularly feedlot cattle in Kansas, Nebraska, and Texas, experience significant production losses when temperatures exceed the thermal comfort zone. Heat stress reduces feed intake, reduces weight gain, reduces milk production in dairy cattle, and in severe events causes direct mortality. The cattle industry lost tens of thousands of animals in a single Kansas heat event in June of 2022, when temperatures spiked rapidly with no overnight relief. The downstream effect of simultaneous crop stress and livestock stress is not complicated to trace. Reduced corn yield tightens the supply of animal feed. Tighter feed supply raises the cost of producing beef, pork, and poultry. Reduced soybean yield affects everything from cooking oil to protein meal. The consumer feels it at the grocery store roughly 6 to 12 weeks after the fields feel it. That timeline puts the grocery store impact of what is happening in the fields right now squarely in September and October. Enjoy the summer sales while they last. I am only partially joking. The coming weeks, what the models are showing here is what the forecast models are currently projecting, and I want to be precise about what model guidance means and what it does not mean at extended ranges. At the 1 to 7 day range, numerical weather prediction is highly reliable. The models agree, the confidence is high, and the forecast is essentially a fact. At the 7 to 14 day range, confidence drops significantly, but broad pattern features, like the presence or absence of a dominant high-pressure system, remain meaningful. Beyond 14 days, you are looking at probabilistic guidance, tendency rather than certainty. With that framing clearly established, here is what the models are showing. The current heat dome over the southwest and parts of the south is projected to persist through at least the first week of July. There is no significant trough, no deep low pressure system, no frontal boundary with enough energy to displace the blocking high that is holding this pattern in place. Phoenix will remain in triple digits. The Southwest will remain in triple digits. The Southern Plains will remain in triple digits for at least another week and likely longer. The more alarming signal in the extended models is not the persistence of the current event. It is the suggestion of a second heat pulse in the second half of July targeting a different part of the country. The ensemble models, which run dozens of simulations simultaneously to capture the range of possible outcomes, show a concerning cluster of solutions in which the blocking pattern rebuilds over the central and eastern United States after a brief and partial break. That scenario would put the Midwest, the Ohio Valley, and potentially the Mid-Atlantic and Southeast into a heat event during a period when they have had no meaningful recovery. Back-to-back heat events with an inadequate recovery interval are measurably more dangerous than a single event of equal intensity. The body, the grid, the crops, the water system, all of them need the overnight lows and the between-event cool periods to reset. If the second pulse arrives before that reset completes, every threshold for harm is lower. The grid is already stressed. The crops are already stressed. The emergency rooms are already seeing elevated heat-related admissions. A second pulse hits a system that is already compromised. The Climate Prediction Center's outlooks for July currently show elevated probability of above normal temperatures across most of the contiguous United States. Above normal does not mean record-breaking. It means the odds are tilted toward warm. In the current context, with sea surface temperatures running significantly above average across the Gulf of Mexico and the Atlantic, with the atmospheric pattern favoring persistent ridging, above normal is a significant understatement of the plausible outcomes. The National Weather Service has prepositioned additional resources in several regions in anticipation of continued extreme heat. That is not a standard operational posture. That is an agency that has looked at the models and decided the normal staffing assumption is not adequate for what is coming. The bigger pattern nobody wants to say out loud. 2023 was the hottest year ever recorded in human history at the time. Then 2024 broke that record. Then 2025 broke it again. We are 5 months into 2026, and the global average temperature anomaly relative to the pre-industrial baseline is running above levels recorded in any previous year at this point in the calendar. I want to say that again clearly because it tends to get lost in the noise of individual events. Every single year from 2023 through 2026 has set a new record for global average temperature 4 consecutive years, and 2026 is currently on pace to make it 5. The global ocean heat content, which is the more stable and comprehensive measure of planetary warming, because the oceans absorb over 90% of the excess heat trapped by greenhouse gases, reached an all-time record in 2025. The oceans are the thermal memory of the climate system. What goes into them stays there. They release that heat back into the atmosphere over years and decades. The heat content record set in 2025 is not an abstract number. It is an energy debt that the atmosphere is currently collecting on with interest. The El Niño Southern Oscillation, which I know sounds like the name of a band that plays at a very specific type of festival, is currently transitioning toward El Niño conditions, with the oceanic Niño index warming toward positive territory. El Niño events redistribute heat from the tropical Pacific into the global atmosphere. They tend to amplify already warm years into record years. If a moderate to strong El Niño develops by late 2026, as current model guidance suggests, it will be layering additional warming on top of a baseline that is already the hottest in the observational record. The scientists who study this, not the ones who appear in cable news segments, but the ones who publish in the journals and run the models, are not ambiguous about the trajectory. They are unambiguous about it. The question they are arguing about is not whether this is happening. It is how fast, and whether any of the feedback mechanisms, ice albedo feedback, permafrost methane release, Amazon dieback, cross thresholds that accelerate the trend beyond what the models currently project. That conversation, the one happening in the literature and at the conferences rather than on the evening news, is significantly more alarming than the coverage suggests. I am not telling you that to panic you. I am telling you that because you deserve to know where the frontier of scientific concern actually sits, rather than the carefully moderated version that gets filtered through 17 layers of editorial caution before it reaches you. The scientists are not calm about this. They are doing what scientists do, which is express their alarm in precise, heavily qualified language that does not read as alarm unless you know how to read it. Allow me to translate. When a climate scientist says the current trajectory is inconsistent with achieving stabilization targets and represents an increasingly narrow window for effective intervention, what they mean, in plain language, is that they are scared and they are not sure the window is still open. What you actually do with this information. None of this is useful if it ends in paralysis. So let me be direct about the practical level. The wet bulb reality check is the most important thing I can give you. If you are in a region currently experiencing extreme heat, the number on your weather app is not the number that matters for your safety. Look up the heat index or the feels like temperature and treat that as the real temperature. If the heat index is above 105 degrees, limit outdoor exposure to the absolute minimum. If it is above 115, eliminate it entirely for the most vulnerable people in your life. The populations at highest risk are the elderly, infants, and young children, outdoor workers with no ability to take breaks in air conditioning, people with cardiovascular disease, diabetes, or respiratory conditions, and people without access to air conditioning of any kind. If you know someone in any of those categories and you live in an affected region, checking on them once is not enough. Check on them daily. The 650 people who died in the Pacific Northwest in 2021 largely died alone, in their homes, without anyone realizing how bad the conditions were inside those buildings until it was too late. Cooling centers work. Libraries, community centers, shopping malls, any large air-conditioned public space functions as a cooling center during a heat emergency. Many municipalities formally designate them. Find out where yours are before you need them, because the moment you need them is not a good moment to be researching. Fans are not air conditioning. This is genuinely counterintuitive and genuinely important. A fan cools you by accelerating evaporation from your skin. When the wet bulb temperature rises high enough that evaporation is no longer effective, a fan moves hot air across your skin and does essentially nothing useful. In an extremely hot and humid room, a fan can actually increase heat stress by increasing convective heat gain from the hot air. Fans are a heat relief tool. They are not a heat emergency tool. Hydration matters, but it matters in a specific way. Thirst is a lagging indicator of dehydration. By the time you feel thirsty in extreme heat, you are already behind. Drink water continuously and consistently, not reactively. Here is where things stand right now. The hottest June in the 146-year observational record just ended. The models are not projecting a return to normal. They are projecting a continuation and a potential second pulse. The infrastructure supporting 250 million Americans in the affected regions was not designed for conditions this extreme, and in several critical areas, it is already showing stress. The agricultural calendar is being written in real time with a heat pen, and the food supply will feel it before summer ends. And this event is not occurring in isolation. It is occurring against a backdrop of 4 consecutive record-breaking years of global average temperature, with the 5th year currently on pace to join them. This is not a summer weather story. It is a systems story. It is a story about what happens when a collection of interconnected systems, the human body, the power grid, the food supply, the atmospheric pattern, all reach their operational limits simultaneously in the same weeks across the same country. The people who watch these systems for a living are watching closely right now, not because this is unprecedented in their models, but because their models have been telling them something like this was coming for years, and now it is here, and the second half of the summer is still in front of us. We will be tracking this closely as the pattern evolves over the coming weeks and bringing you updates as the models sharpen and the conditions develop. Because this is not a story that ends when the heat dome breaks. It is a story that is just getting started. Welcome to the new summer.